Good afternoon. My name is Saif Islam. I'm a professor of electrical and computer engineering at UC Davis. I'm also the director of CITRUS at Davis. Welcome to the 40th year of the CITRUS Research Exchange Seminar Series. We have hosted a remarkable lineup of technology innovators in person at Sutardja Dye Hall, and are glad to see all of you are joining virtually today for the Spring 2023 seminar. Before we begin the talk, I want to first highlight a few upcoming events. The next CITRUS Research Exchange will be held on Wednesday, February the 8th from 12 to 1 p.m. Pacific Standard Time for a discussion on bioconvergence, transforming how human live and age, with Stephen Johnson, Vice President, Head of Technology Transform and Implementation, Mark KGAA, Darmstadt, Germany. Please be sure to check the CITRUS webpage for registration details and further updates. Join Agintech, CITRUS and Bonatow Institute and Berkeley Engineering on March the 2nd for Smarter Tech for a Resilient Future, a virtual symposium highlighting the experiences of experts using emerging technologies to advance innovations for more sustainable infrastructure. Virtual presentation participations guideline. Before going into the talk, please post your all questions and answers in the Q&A box on Zoom. You should see a Q&A icon on the Zoom toolbar. Clicking the thumbs up on the question will help bring it to the top of the Q&A window. Questions will also be addressed at the end of the talk. Today, we are joined by Michele Barbato, who is a professor of civil and environmental engineering at UC Davis. He's a co-director of UC Davis Climate Adaptation Research Center and the director of CITRUS Climate Research Initiative. He's a licensed professional engineer, PE, in Louisiana and in Italy. Dr. Barbato's research aims to develop safer, economic, and more rational design procedures for sustainable infrastructure and resilient communities. He's the author of more than 200 technical publications. He received the 2020 ASC Sacramento Section Frederick Panhost Structural Engineering Award, the 2020 Walter L. Hoover Civil Engineering Research Prize, and many additional research, teaching, and service awards. He was elected a Structural Engineering Institute Fellow and Engineering Mechanics Institute Fellow by the American Society of Civil Engineers, ASCE, in 2019 and an ASC Fellow in 2021. It's my great honor to welcome Professor Michele Barbato.
Thank you, Saif, for the very nice introduction, and thank you, CITRUS, for inviting me to this very interesting research exchange series of seminars. Today, I'm going to talk about some of my research on climate change and how that affects building, construction, and houses in the United States. So let me see if I can share my screen. Just before I start talking, I wanted to make sure, is it visible? Saif,
it is, we can see it.
Perfect. Thank you very much. So I'm not going to reread everything here, but the title of the presentation is Climate Change Effects on Hurricane Risk for Single-Family Houses in the United States. This is a brief outline of what I will be discussing today, some introduction on climate change, a background on hurricanes, and then I will enter more into the details on how to model climate change effects on hurricane wind loads. I will introduce some concept of performance-based hurricane engineering, and then I'll use the performance-based hurricane engineering framework to assess the effect of climate change and structural aging on single-family houses in the United States. I will also draw some conclusion on where we go from there. starting, the basic concept is we live in a period with a non-stationary climate. Climate change is changing. Climate is changing. That usually means the temperature are increasing. And this trend of increasing temperature has an effect on the environmental loads that are present and that are affecting our built environment. In practice, what we are observing is that the frequency of climate-related disasters is increasing. And here in this slide, you can see the number of events and the amount in terms of cost and losses produced by different climate-related disasters. In this slide, the green and the yellow correspond to severe storm and to tropical cyclones. And as you can see, these are the ones that are increasing in number more rapidly. So why are we seeing this? There are several reasons, but in order to understand that, we really need to go back to what hurricanes and tropical storms are. And you have probably heard different names for the same things. Hurricanes here in the United States, typhoons in Asia, cyclones in Australia and Oceania. These are fundamentally tropical storms that are formed over tropical oceans. They can be extremely large. The largest recorded is Cyclone Tip in 1979 with a dimension of more than 2,000 kilometers, about 1,300 miles of diameter. These are storms where the sustained wind speed is higher than 74 miles per hour. They have been typical again in United States, in Asia, and they are starting to appear even in the Mediterranean Sea, where there are no other records than the one that we have in the last 20 years. So what is it and how do these things get generated? Fundamentally, the necessary condition for development of hurricanes is warm ocean waters. They need to have a temperature that is higher than 78 Fahrenheit. They need to be sufficiently north or south than the equator. They need to have a situation with low vertical wind shear so that the wind is not disturbing the formation of the clouds. Moisture in the mid-troposphere, some unstable conditions, and some disturbances. Fundamentally, from a physics point of view, what happens is that the warm water produces moisture that is bringing up energy in the troposphere, where this hot vapor is meeting cold and stable air, and then this is producing fundamentally is the engine that starts the rotation and is producing also all of the rain that we see with this type of events. So the higher is the temperature of the water, the stronger tends to be the hurricane. In terms of intensity, you may be familiar with the Saffir-Simpson hurricane scale, which is used here in the United States to categorize different hurricanes into 5 categories. This categorization is based on the maximum sustained wind speeds, and it's known to have limitations because it doesn't account for other important effects that are connected with hurricanes. For example, the formation of a storm surge, the amount of rain, and these kind of things. Also, it's difficult to really stand behind the definition of damage as minimal, moderate, extensive, extreme, and catastrophic, because even hurricane category 1s can have a very large effect in terms of damage and in terms of costs and loss of lives. Anyway, this is the current categorization that is fundamentally based on the sustained wind speed. But let's analyze more in detail what are the effects and the actions that are produced by an hurricane event. So these are the ones that can produce damage on structures. Obviously, strong wind is the most obvious type of load that is produced by hurricanes. Fundamentally, the movement of the fluid air produced by the wind produces a pressure on the surfaces of a building or on another structure. This pressure produces a force. If the force is too high and damages the structure, then the damage can get different level of damage, can be even destroyed. Another type of effect that is connected with hurricanes is windborne debris. These are objects that are lifted by the high wind speed and are projected against other structures and buildings. And the effect of windborne debris is more severe than just the local damage produced by the penetration of a missile, which is already quite severe and dangerous. It is worse because once the envelope of a building is breached, it produces an internal pressurization. And so very often we see houses damaged by hurricanes that look like they exploded. The reason for that is a breach in the envelope and then the pressurization inside that makes the roof blow up and all of these other things. Then the other extremely important effect is the one of storm surge that can produce coastal flooding. This is really the most dangerous effect in terms of potential loss of life because once there is this very severe flooding produced by the storm surge, it's fundamentally impossible to evacuate. And so that's extremely dangerous for human life. Finally, rain, a cause for flooding and one of the major effects in terms of losses for the content of the houses. Once rain and water are penetrating in the house, there is always a very large amount of losses associated with that. So now that we have an idea of what generates an hurricane and how an hurricane affects a structure, we can enter more into the details of how climate change affects that. Clearly, we have seen that the temperature of the water is the main engine for the energy and the intensity of a hurricane. What we have observed with climate change is that the global sea surface temperature has increased significantly in the last 100 years. And so what we have also observed is that in general, the hurricane intensity have increased during the same period. Not so much the number of hurricanes, and thus the frequency, but the intensity of the hurricanes that are making landfall is increasing. However, we need also to point out that it's not only a question of increasing of intensity of the hurricanes. The risk that we are bearing due to hurricanes is increasing not only because the hazard is increasing, the hurricane intensity is increasing, but because we are also increasing our vulnerability. And in fact, the combined issue is that we have more and more people that are living near the coast, in places that are prone to hurricane damage. And so we have more people, more valued good and infrastructure that is in places that are vulnerable to hurricane effects. And so we get really what I would like to call a double whammy, because on one side we have the hazard that is increasing, on the other side we have the vulnerability that is increasing, and our risk is increasing extremely fast because it's the product of these two effects. And this is clear when we look at how the temperature is increasing and in the same period of time, how the losses associated with hurricanes are increasing. The losses are increasing much faster than what would be connected only to the hurricane intensification and the intensification of the effects of hurricanes on structures. So what we need is a better understanding of how climate change is affecting hurricanes. We really need a projection model for future wind speeds. We need to be able to predict how wind speeds will change so that we can design our structure for the next 50, 100 years instead of relying on information that is representative of our last 50, 100 years. To do that, we need to use a probabilistic approach, but we also want to be consistent with the current approach that is using wind maps to describe different mean return intervals that are used for design. We need also to be able to predict not only the average changes in wind speeds, but also the extreme changes in wind speeds. The method should be as easy as possible to use, computationally efficient, and it needs to be as possible consistent with other models that are using a physics-based approach, but also nimble enough that we can evaluate the effect of different climate change scenarios. This work is something that I did with a previous PhD student of mine, and has been published. And so I will present very briefly the work that we have done and the proposed predictive model for hurricane wind loads under changing climate conditions. Our starting point was the information provided in the fifth assessment report in 2013 by the Intergovernmental Panel on Climate Change, which provided us the input in terms of expected increases in sea surface temperature and seawater level. The sea surface temperature are the data that we use to evaluate the effect of the wind, the effect of climate change on the wind, while the seawater level is what we are using to assess the effect of storm surge. In this presentation, I'm going to focus exclusively on wind and windborne debris. So we are going to use only the sea surface temperature. With this information, we decided to use a statistically based projection model with identifying what we call intensity measures from historical data. These are parameters that are used to describe physically in a parametric method the different hurricanes. And these are the hurricane annual frequency, the peak hurricane wind speed, the radius at peak wind speed, and the central pressure deficit for a given hurricane. Using historical data, we identified the frequency changes as a function of time and as a function of the annual average of temperature. We found that in reality, which is also consistent with the observation, there is very little, if any, change in the hurricane annual frequency. And then we correlated the temperature at the time and location of a hurricane with the average temperature of a given year, again, using historical data. The reason to do that is that it's the parameter that is really controlling the intensity of the hurricane is not the average temperature of Earth in a given year, but is the temperature at the location and time where the hurricane is forming. And so we did this investigation that is region dependent for the Gulf Coast and for the Atlantic coast of the United States. With this information, then we related the other intensity measure, the other parameters that are describing an hurricane with the temperature. Again, using a very simple linear regression for each of these variables. Once we have these parameters, we can simulate the intensity and the location of a hurricane. But then we are interested in seeing what these hurricane effects are on a given location, on a site where we want to build a structure. So what we did was repeat this analysis along all of the Gulf Coast and Atlantic coast of the United States, from Texas to Maine, at 100 miles intervals. And for each of these locations, we were able to define a radius of influence that is the area around the site where a passing hurricane is going to have an effect on the local wind speed at the site. Again, I'm not going to enter into all of these details, but once we have this information, we need to be able to transfer the intensity of the hurricane into a wind speed at the location. And we did that by using the so-called Willoughby model that provides a wind speed profile based on the parameterization of a given hurricane. And by combining the rotational wind speed with the translational wind speed of the hurricane through the George model, that is the equation in the bottom of this slide, we are able to evaluate or simulate and sample the wind speed produced by a hurricane at a given location. If we repeat this process a very large number of times, we are able to build a distribution of wind speed, of annual wind speed at a given site. And from that one, we can estimate the loads that are applied on a structure that is built at that location. So once we have this model, the first thing that we wanted to do was to validate it. The first layer of validation is with the historical data. We started with the historical data in the NIST database, which is able to provide us the mean wind speed and the standard deviation of the wind speed at the given location for the time period between 1871 and 1963. We used our model and we predicted or estimated the mean wind speed and the standard deviation of the wind speed corresponding to the average temperature during the time period of analysis. And what I'm presenting here is not only the numerical values, but also graphically the comparison of our simulated average and standard deviation wind speeds with the one that have been estimated from historical data. And we can see that there is a very good correspondence between the simulated data and the historical data. In fact, if we look at the average error between the simulated data and the historical data, we have that both the mean and the standard deviation differ by less than 1%. So we have 0.68% error in average on the mean wind speed and 0.07% error in average for the standard deviation. So once we got this type of data, we start having a little bit of confidence in our model that is able to reproduce the body of the distribution in the past. But we are interested not only in the mean and standard deviation, we are interested in the stream. And so we further validated our model by considering the 4 mean return intervals that are used in a C7 for the design of different structures. These mean return intervals are 300, 700, 1700, and 3000 years return periods that are used for buildings of risk category 1, 2, 3, and 4. Just to give you an idea, a risk category 2 is a normal building and corresponds to houses, commercial buildings, residential buildings that are with less than 300 people inside. So typically a building is designed for a wind speed corresponding to a 700-year event. So what we did, AAC data fundamentally represents the historical data in streams for the time period between 1886 and 2010. And we used our model to predict the same type of extreme wind speeds. We did that again at the 27 different mileposts along the Gulf Coast and the Atlantic coast of the United States. And again, we found that in average, we make an error that is always less than 1% for each of the different mean return intervals. So now we start having even more confidence in our model, but so far, we have only demonstrated that we are able to predict the past. So we are really interested in predicting the future. So what did we do for further validation? We compared the results of our model with the one of other more expensive, more complex models that are available in the literature that are using the hurricane tracking and climate downscaling to estimate how the extreme values of wind speed are changing as a function of the mean return interval. And there are two models that were available at the time of this paper, the Cohen-Caracollia model and the Pant and Cha model. And here you can see that fundamentally the three models are giving the same type of results for different projections, different scenarios. These are the projections corresponding to the worst case scenario, RCP 8.5, and the best case scenario, RCP 2.6, for year 2100 in Miami, Florida. So we are extremely happy of this result because our model, with difference of the other two, is 1,000 times faster and allows us to evaluate many more climate scenarios and conditions and locations at a fraction of the time that it takes to run a physics-based model. So now that we have more confidence in our model, we are also able to start projecting the wind speed in the future. And that's exactly what we did. Here I'm presenting the projections for year 2060 and the worst case scenario at the different mileposts along the Gulf Coast and the Atlantic coast of the United States. These projections are first for the mean and the standard deviation. And so what we see is that overall, we have a mean wind speed increase between 7% and 10% over the coast. And the standard deviation has an increase that is even larger. That's kind of obvious. We have more uncertainty, so the variability is increasing more. And again, this variability is between 10% and 13%. Now, this may seem a small amount of increase, but again, if we want to know what is the real effect on the design of structure, we need to look again at the design wind speed at 300, 700, 1700, and 3000 years. So we did the same exercise in this situation. And what we found is a little bit scarier because we are seeing a design wind speed that increases by 12 to 40%, depending on the location and the mean return interval. Now, the design wind loads go with the square of the wind speed. And that means that we are actually looking at an increase of the design wind loads that is between 26 and 95%. 95% increase in the load is a huge amount of additional load that we are not designed for. And so what we are doing right now is really designing structures that would have survived the last 50 years, but will have a very big difficulty in surviving the next 50 years, which is when they will be actually built and we'll have to take these new wind loads. So what can we do to improve our situation? There have been different approaches that have been suggested to address climate change, particularly for wind speeds. The easiest one is updating the basic wind maps to account for climate change. This is the easiest because it keeps the same format that is used currently by structural engineers. But there are some questions and issues that need to be resolved in order to use this methodology. For example, what year should be used to update these maps? Different years will have different maps because they are changing as climate is changing. What scenario should we use? And how many maps will be needed in order to address the needs of structural engineers? There is also the possibility of using a climate change amplification factor. Again, this is something that has main advantage is that is similar to methods that are currently used by structural engineers. But again, we have factors that are changing from place to place. They may change with time, with risk category, and they may also change with the service design life of a structure. Is a structure designed to resist for the next 50 years, for 80 years, for 100 years? All of these would require a different amplification factor. The most rigorous method for analysis is the reliability-based design. However, this is a complex method that requires very in-depth understanding of climatology, risk, nonlinear finite element modeling. It is currently not used for common design. Is really a methodology that is used more for calibrating simpler approaches that are proposed in the design codes and standards. Another possible approach that kind of ends in between the basic wind maps and the reliability-based design is the performance-based design, which is a methodology that is getting more common, at least for important structures, that is still able to account in a rigorous manner for the different sources of uncertainties, and that has a better chance of being used for real structures. And a lot of my recent research has been focusing on developing a performance-based design approach that can be used for structures subjected to hurricanes and other hazards. In fact, some of this work led to the development of a performance-based hurricane engineering framework that is based on the total probability theorem. I will show in a little bit what that means. Also, this framework is different from the other performance-based design framework because it represents the first multi-hazard framework. We have seen that in hurricanes, you need to really take into account the effect of wind, windborne debris, rain, and storm surge. It is a generalization of performance-based wind engineering, and it includes different types of hazard consideration. In particular, is focusing on synchronous hazards because wind, windborne debris, rain, and storm surge are all happening at the same time. And also on cascading effects, because the damage that is produced by one of these hazards can trigger and increase the effect of other hazards. One of the examples that I made before is when there is damage to the envelope of the building due to windborne debris. then this also changes the internal pressure of the buildings, thus increasing the effect of the wind hazards. So how does this framework look like in a mathematical sense? It may look a little bit scary because it's a quintuple integral of all of these random quantities represented by conditional CDFs, cumulative distribution functions, and probability density functions. But really, what is the concept? The concept is what I like to call divide and conquer. We have a complex problem and we are breaking it into simpler steps that can be addressed by people with different expertise. So we have a first step that is the hazard analysis that considers the climatology and the weather characterization of a given location. The structural characterization that identifies the properties of the structure that can affect the loads applied on the structure. The interaction analysis that puts together the local hazard and the characteristic of the structure to evaluate probabilistically what are the loads applied on the structure. And then the structural analysis, that is what usually structural engineers do, transform the loads into the response of the structure. A damage analysis that connects the response of the structure with the damage observed on the structure. And finally, a loss analysis that evaluates the losses in terms of money, reduced use, closure time, or life losses derived from the damage produced on a structure. In addition, we have a loop that allows us to change the properties of the structure as the structure gets damaged by the hurricane event. So if you are familiar with performance-based earthquake engineering, you will see that there is a very strong similarity between the methodologies. And the part that is different is the one that is surrounded here by this red line, where this allows us to consider multiple concurrent hazards and the different way that they are affecting a given structure. In order to use this methodology, we had to also find a way of implementing it. And the one that we are using and that I'm going to present in this presentation is the multi-layer Monte Carlo simulation, fundamentally a methodology that is based on stochastic simulation, where each of the steps of analysis in the performance-based hurricane engineering framework is broken into two sub-steps. A first step that is a sample generation or a stochastic simulation, and then an analysis step that is generally based on deterministic model that are used to propagate uncertainties from one step of the methodology to the next one. So what are the type of results and uses that we get from this type of methodology? I'm going to present very quickly a case study that focuses on an individual building in a real residential development in Pinellas Park, Florida. This is a gable roof structure with shingle covers. We made some assumptions in here with the value of the base structure and the value of the content respectively assumed as $200,000 and $100,000 at the time of construction of this house. If we look at the unfolded view of the target building, it is a rectangular building. We have removed from the building the attached garage for simplicity of analysis. That's the location, some of the geometric parameters that characterize this building. So we go through the entire methodology presented before. I will not describe each individual step again. I'm just going to look at the limit states that we are considering in analyzing this structure. So the things that can go wrong. We can have damage on the roof covers, the shingles can detach, so there is separation or pull off. The sheeting in the roof can also separate or pull off. The doors can be damaged by pressure. The windows can be damaged by pressure or impact. The roof wall connection can fail due to tensile load applied to them. And then the walls can fail due to lateral failure or to uplift. All of these characteristics and probabilistic distributions to describe the strength of the different components are available in the literature, were adopted from the different publications that investigated each individual limit state. So how does the result of our analysis look like? It is generally expressed as an annual probability of exceedance curve that is giving on the vertical axis the probability of exceeding a limit state or a damage, and then as in the horizontal axis is the corresponding loss that is happening with that given probability. If you take the area under all of these curves, that is fundamentally the estimated expected annual loss corresponding to a given building subjected to a given hazard. In this case, we actually separated the different sub-hazards to see how they are interacting. The hazards that are considered are the wind coming from hurricanes, wind coming from non-hurricane events, and then the debris coming from hurricanes. The windborne debris coming from non-hurricane events have an effect that is negligible and doesn't appear in this curve. Among the interesting things, we find that the interaction of all of these hazards is actually worse than just the summation of each individual hazard. In fact, if you take a look at the values of the expected annual losses for each individual hazards, you sum them up, you obtain a value that is smaller than actually the expected annual loss corresponding to all of the hazards happening at the same time. So how do we use this? We used it for a cost-benefit analysis of retrofit, considering 4 different strategies: use of aluminum hurricane protection panels for the windows, changing the shingle as roof covers into clay tiles, using stronger nailing patterns in the roof sheeting, and then a drastic change of using masonry walls instead of wooden walls. A combination of a total of 24 different possible conditions, again, allowing us to do this analysis because our model for wind speed is extremely effective. We are calculating the benefit of each retrofit, which is fundamentally the summation of the reduction in damage that is discounted in time minus the initial cost of retrofit at present time. Here, all of the results are presented for a design life of 30 years and assuming a discount rate in average equal to 3% over the design life. So the results can be presented in this tabular form or in histograms, where all of the data that are above the 0 line corresponds to a benefit of making a given retrofit, and everything that is below that line corresponds to actually a cost, an initial cost that is more than the saving that we can have during the lifetime of the structure. Obviously, these results depend on the structure, depends on the location, depends on the type of climate that you are considering. But just briefly, it allows us to identify that for that specific structure, the 2 retrofit solutions that are most effective are increasing the strength of the roof sheeting with different nailing patterns, better nails and more dense nails, and then very cheaply using storm panels to protect the windows. Okay, so all of these is fundamentally really related only to hurricanes and independent on climate change. So what we did was expanding our method to account for the effect of climate change and this non-stationarity in time of the actions. This is the new format of the PBHE framework, where we have an additional integration related to the presence of these climatological conditions that are really describing how climate is affecting the load applied on the structure. The example that I'm going to use is the same as the one that we have seen before. So we are still considering the same target house in the same residential development in Pinella Park, Florida. And we did a little bit of investigation of what happens when we consider different climate conditions. So we reported here the expected annual losses and the standard deviation of losses a different period of time under different climate conditions. As you can see, in different scenarios, the typical effect is always an increase in expected annual loss and an increase in the standard deviation of losses when compared to the reference time that was 2015 for this building. If you evaluate the mean standard deviation of the total losses in a period that goes from 2015 to 2065, so 50 years of life for that building, you find that you can have just due to climate change an increase up to 38% for the worst case scenario of the expected total losses for your building. Then, now that we know the dependency on the climate scenario, we investigated also the sensitivity to the different location. And you can see here, we did this analysis for all of the 27 different locations along the Gulf Coast and Atlantic coast. And there are some places that are really jumping to the eye. So our initial analysis is in Pinella Park, that is identified by this vertical dashed line. But you can see how the cost of hurricanes can change a lot depending on the location, with the New Orleans and the Florida Keys and Miami that are obviously jumping to the eyes as very, very high losses. And all of these is accounting only for climate change. So there is another problem. Our houses are not only getting more load due to climate change, but they are also getting older. And getting older means that they are decreasing their strength. So I'm not going to enter into all of the details of the aging model that we have used, but we have considered the effect of aging models on the roof-to-wall connections, on the roof and wall sheeting, and the roof covers, all data from the literature. And so what we did was comparing what happens to the given house in Pinella Park when we assume that there is no climate change and no aging, when we assume that there is only climate change, and when we assume that there is both climate change and aging. And these are the results of our analysis. We found that the effect of climate change by itself is it can be as high as 38%. The effect of aging by itself without climate change can be as high as 33%. But then when you put them together, the expected total losses for a given house in Pinella Park are increasing by 97%. That's fundamentally double the loss that we get if we neglect the effect of climate change and we neglect the effect of aging. So I'm going to conclude very briefly. We have seen that climate change affects wind loads, in particular hurricane wind loads. We have developed the probabilistic projection model that is able to reproduce very well past wind speed, both average and extreme, and we are using it to estimate the changing climate conditions in terms of hurricane wind speed. We found that we can expect, in the worst case scenario, an increase of the basic wind loads used for design that is as high as 95%. We have seen that there is no consensus yet on how to account for climate change, but we have proposed an approach that is used on performance-based hurricane engineering for wind and hurricanes. And this framework has been applied to single-family houses subjected to hurricane hazards, showing a type of application and use that we can have of this framework. And that's been then extended to include climate change and structural aging. What we think that this performance-based hurricane engineering method is most useful is to develop not only a design method, but also for different types of structure, but also can be used for calibration of the standards so that other methods that are simpler can also be used to account for climate change and aging effect on structures and housing. And I'd like to conclude with some acknowledgements for all of the funding agencies and the people that have contributed to this research. And with this, I'd like to thank you very much for this opportunity to talk about my research. And I'll be very happy to respond to any question you may have. Thank you.
Thank you, Michele, for this great talk. Seems like there is a lot of bad news, but the good news is there are researchers who are on top of the problems. While we await questions from the audience, I would like to quickly ask, here in California, most of us directly experienced firsthand climate change, impact of climate change. The building where I am in now got damaged by a big tree that broke a corner of the building. This is a very professionally built, extremely durable building, but it also lost a small portion of a wall, couple of windows. And I guess a number of homes completely got destroyed here in Northern California. Now, if the situation continues to get worse, if wind gets even more wilder, I guess all of us will probably have to make some modification to the current structures while we also think about building with new codes, new kind of regulations. You mentioned some of those. Could you maybe summarize? If I'm planning to build something in the next 5 years, what would I expect in terms of regulations and codes and methods that you'll have to implement?
Yes, that is a very important question and has a lot of implications. What I can say is that most of the buildings in the United States are designed against wind by using the so-called AC7. This is a standard that provides the minimum design loads that need to be used for earthquakes, winds, snow, water, flood, all of the different conditions that the building can be affected by during the life. Unfortunately, the current situation is that we are using only historical data to recommend the minimum loads that we need to design for, which fundamentally means we are really designing for the last 50 years of history, not for the next 50 years of future for which we should be really designing. We are working right now with the AEC, NOAA, NIST, and all of the different USGS, all of the different agencies, federal agencies that have information on climate to cover this gap, to have a new version of AC7 for 2028 that will at least acknowledge the fact that we need not only to use historical data as we have done so far, but we need to start using also projections so that we can properly design structures that are safe for occupants and for society in the next 50 years. So I don't expect a lot of changes until 2028 because it takes some time to arrive to something where everybody is in agreement. But I really hope that in 2028 we will start having a better control on this issue. And so what I suspect we will be doing is, at least for important structures, we will be considering climate change from the next round of new standards overall for the United States. Canada is ahead. They've been doing this process since 2015, and they will have their first code accounting for climate change in wind, snow, and flood starting from 2025. We are a little bit behind, but I'm sure we'll be catching up soon.
Okay, thank you. We have one question here from the audience from Lyle Carden. Have you or do you intend to apply your model to changes in hurricane hazards in Hawaii? I'd like to get those conclusions if available now or in the future.
I think that would be a great idea, not only for Hawaii, but also for Puerto Rico. The intention is there. It's just that it is a quite intensive data analysis and time commitment. And it would be great to be able to do it, but there is always the limitation of funding and time. So that's one also the reason that I'm working with the federal agencies, because maybe it could be overall a more effective way of doing things if people that are working in climate science and have all of the data available and the resources available are going to be providing this data to engineers. But I definitely would be very interested in doing this type of analysis for Hawaii and Puerto Rico and the other islands in places that are connected with the United States.
Okay. I think we have time while I'm waiting for, actually there is a new question. Does the aging model start with a new home today? This is from Gabriel Carvalho. Does the aging model start with a new home today? So
the way that we model the house, we assumed that the house was built in 2015. We used the information from the standards of 2015 to characterize the initial properties of the structure. And then we started our aging process. I didn't discuss that in details in the presentation, but we actually considered an aging model that is independent on climate change and one that is coupled with the climate change. The way that we assess the aging and the damage is that the aging is progressive until an element is too damaged and needs to be substituted, and then whenever a component needs to be repaired or substituted, the aging process restarts with the new element. So the aging that I presented here was starting from a new house in 2015, and then the aging process was continued for the 50 years from 2015 to 2065 with the current aging at different times. I hope that responds to the question.
Thank you. Thank you. I have a quick question. So people say the temperature of the planet increased by a degree and that caused so many new climate-related issues. I'm sure you have a quick answer. If, let's say, temperature increases by another 2 degrees, what do you think will happen to all these hurricanes and storms and situation? Will this be an unlivable kind of planet?
It's not going to be pretty. The issue is that we are talking about 1 degree, 1.5 degree, 2 degrees. These are average increases over the entire planet, averaged over a year.
Right.
But they have much bigger effects in terms of extremes. So you can expect much higher variation on wind speeds, snow, water level, all of these kind of things. It is really progressing in a much more rapid way than the average temperature. In addition to that, we are looking not only at events, but we are looking at extreme events, and their variability will be even higher, which means that the peaks will be much higher than what we have. So an increase of 2, 3, 4 degrees can be really catastrophic if we do nothing about it. And I don't think that we can really use an approach of only adaptation at that point. We really need to work together and have a positive adaptation that synergizes with mitigation. If we don't do that, then I don't think the planet will be unlivable, but we are talking about hundreds of millions of people or billions of people that will have to move from where they live now in order to find a more livable situation. And that is extremely dangerous. Not only is terrible from a human point of view, but is extremely dangerous in terms of political stability. And that is really what scares me the most, because if we arrive to that point, then the bets are off. I don't think climate change by itself would be enough to extinguish the human race, but it could be the trigger for us doing that type of job. And I would really not want to be there.
Okay. Thank you very much. This was such a great discussion. I think there is a comment. Thank you, Amar Chakar. So if there is no other question, or we are close to the end of our time now, thank you, Michele, for making time and for such a great talk. I think just like food and shelter and clothes that human beings need, I guess everything is going to be impacted by all these roller coaster climate. Our homes are impacted now, so shelter is going to be a huge problem. Hopefully, we will not have to face even more severe crisis, and scientific activities will contribute to a solution, and people will continue to implement those. Thank you, everyone, for joining us today, and thank you, Michele, for this great.
Thank you very much. Let me just add, if anybody has later questions, you have here my contact information by email, my webpage. If you have additional questions, please do not hesitate to contact me. And thank you again, Saif, and everybody at CITRIS for this opportunity to present my work on climate change.